everyone, welcome back to my math teaching online today. Today is a beautiful day outside. It's the snowing day, but in my hometown, the snow falling down to the pine trees and on the mountains surrounding. I just found it's breathtaking. But anyway, the way I'm showing you the lesson today, before I show any lesson, even though when I was in my classroom teaching, I always chat a little bit with my students, just to have a little bit soul talk. Well, that is my way. I hope that you still enjoy my video teaching, regardless which way I'm doing it. Okay. So let's talk about the topic of the lesson now. I'm going to read out loud the question to you. And the lesson today, we're still doing volume of solid revolution. I have shown you how to generate it about the x-axis as well as about the y-axis from my previous videos. In this video today, we'll get back to generate revolving about the x-axis. So we review a little bit. However, the cross-sectional area today will be the rectangles. So I remember we were talking about the volume solid object revolving around the x-axis as well as the y-axis, but the cross-section we were dealing with it before was a triangle, and today we do a rectangles. So let me show you the question. So I'm going to read the question out loud to you, right? The base of a solid in the xy plane consists of the region between the two parabolas, y equal x squared plus 3 and y equal minus x squared plus 11. Find the volume of such a solid whose cross-sections are rectangles that have sides lie in the xy plane, which is 4 times longer than the other side. So before I progress through the lesson today, I'm going to show you which points, when we read through the information, which kind of sentence we should pay attention into, right? So the first thing, I will pay attention to the two curve here, which is y equal x squared plus 3, which is this curve, and y equal minus x squared plus 11, which is this curve. What else do I pay attention? I also know that I will have to generate it along about the x-axis, not the y-axis. And what else do I pay attention? Another I pay attention is knowing that we're going to slide through the object by the slice. So remember, in the other section before, we're talking about this method, which is we do derivative first. We will slice this through so many slice sections, and we call a cross-sectional area in the shape of a disc, which is a circle. But today we will do the same technique of this method. We slide through it, but instead of using the shape of the circle of the disc, we're going to use the rectangle shape. So we slide it in the rectangle shape. Now, why do we slide them through? Sometimes it's this, and sometimes it's a rectangle shape. I'm not sure. I think that maybe it should be depends on the object, right? And sometimes it's easier to slide them in this shape And sometimes maybe it better slide them in the triangle shape or rectangle shape. So that's why we learn all of the techniques, how to do it in a different way. Now, the cross-sectional area we doing in here is the rectangles. So we're no longer talking about the area of the circle, right? Of the slice of in the shape of the disk, which is pi r squared. But we have to use the formula of the area according to the slice we slide through, whatever it is, a triangle or it is a rectangle. So the topic today is the slice we cross, we cut it, through it, will be a rectangle. So let's see what we can do about this. Let me explain the diagrams to you one more time, right? I just go through it very quickly, so now I'm going to explain it more details, right? So first, I sketch the two curves here. So my first curve is y equal x squared plus 3, which is the parabola opening upward. And I call this y1 equal x squared plus 3, right? And you can see that the minimum point here across, this is the 3 value, this is number 2, okay? So I scale from here to here 2, and from here to here 3. So this is the parabola opening upward, shift up by 3 units. And I guess at this level, you all know how to sketch this parabola. We went through it through Mark 10 already, right? So I explain a little bit just to remind you, right? So the second parabola will be opening downward because we have a negative x squared here, adding with 11. So it cross, it shift up to the y-axis at 11 value, right? So this is 12 and this is 11. Its scale here is 2, 4, 6, 8, 10, 12, right? 11. So I sketch the two parabola, and of course they will meet at 2 point intersection. I mark the 2 intersection point because that's important, right? Now I also inside, I draw in a 3-dimensional shape that I can visualize it, but I use a dot, right? And I draw the rectangle here, another rectangle here, another rectangle on top represent it, not just 3 of them, but we're going to slide through it so many of them, right? Our cross-sectional area today will be rectangle, but we're going to cut through the body of the object, so many of them, right? And remember, under the concept of real-momentum sum method, when we add the total area, the more slice we slice, the more strip we go slide through, the more accurate of the shape will be, right? If we estimate them under the rectangle, add them together, find the total area. So that's similar idea, except that we do it in volume. Now, so the first step I'm going to go through with you will be so I'm going to mark here solution. Now I haven't drawn the whole shape of the object here, right? Because I think that I'm not sure how it looked like when actually true 3-dimensional object. If we have a computer software and we generate it, it would be very nice and would be look fabulous, right? However, because we do it in hand, everything here, so I haven't drawn the object if we generate, right? But I guess it could be something like the shape of the oval, like the shape of the region on top, right? So something around that. And at the bottom, maybe we have something like this. Now, this is my guessing. could be after we generate, it could result in some object like that, look like that, right? But I'm not sure, so I'm not, and we don't have to worry about what actual the shape of this look like. All what we do is we be able to sketch the function by the data given to us, at least to the point that we can identify some data important and to be able to solve the problem. So that's our focus. I just give you a rough idea of what does the object look like if we generate it along the x-axis, right? And this is not so important actually. But let's solve the problem now, right? So the solution, first solution, I think we're going to talk about the volume, right? We're going to find the volume. And the general formula for the volume of any object is always volume equal the base area, which we call the cross-sectional area in here, right? Cross-sectional area times with delta x, which is the height, right? To form the volume, because we're talking about the three-dimensional. So area gives 2 dimensions, come with another 1 dimension, so 3 dimensions, and make a volume become, right? So that is a general formula for any shape, any objects. Now, I'm going to talk about the cross-section area. How do we find the cross-section area? So volume equal, I'm going to substitute this by an area of a rectangle, because that's what it says. It says that we're going to slide this cross-sectional area by the shape of the rectangle, not the disk, right? In the disk method, we do it by the disk, but this time the question asks us to do it in the rectangles. So I'm going to substitute the cross-sectional area by the rectangle, right? So we're going to find the cross-section area of this rectangle times with the delta x. So now I'm going to substitute the volume of our cross-sectional area, and the formula of the cross-sectional area of the rectangle is not pi r squared, but it's length times width. So I'm going to say going time be length times with the width, times with the delta x. Now, keep in mind that none of these are the fixed number for us to substitute in, figure it out, right? Other than that, we will do it in the lower level, which is in the elementary. We substitute number in and then we figure it out. But unfortunately, we do it in calculus, which is the rate of change, which none of these variables here are the fixed number. They aren't variables. They represent a function. Right? So we have to figure out the way they represent by the function. So what is the length? Let's think about it and let me explain it to you, right? What is the length of our cross-sectional area here? If you look at on the bar diagram here I draw, I did it with the purpose that I don't draw just one rectangles, right? I have 3 rectangles with different 3 shapes here. And you can see that the one in the middle is bigger, but the length is longer, right? The length is longer. And the one at the bottom and the top is smaller with the length, and the width is smaller. Now, why these rectangles are changing like that? Because remember, they were shaped by the 2 curves here. So whatever the curves here will shape the length of it, it will shrink on the length shorter down at the bottom and up on the top. But in the middle, right, it will make it longer because the slide will cut through, right? Each of the slide here will have a different length of the rectangles. So remember, this length here is supposed to be a function of change, not the fixed number. So we're going to figure out how do we find the length here in terms of the function. So here is the key points of our volume of solid revolution, right? The key point here is we have to use our imagination a little bit to realize that the length here and the width here of our rectangle to form its area are the changing object. This rectangle will shape it sometimes small, sometimes big in the middle, and sometimes small on top due to the shape of the two functions. One is above the region and one is below the region. The region here we want to generate it, right? So therefore, the length here and the width here, we have to find it in terms of the function, not in terms of a fixed number. So I'm going to substitute the length here by the function. But what is the function we're talking about? We have two functions here. Which one we're talking about, right? Now we can do it separately by generating the region under the big curve here, the above curve, and generating the region below the small curve, and then subtract it. But I'm going to do it in short form. Instead of do them separate and subtract like that, I'm going to join them in a way that our imagination understood that the length of its cross-section and the width of this cross-section under the subject of change, the rate of change, and we call it calculus. So how do we know their length and how do we know their width if there's so many of them, and which function we're going to use? Remember, if you do separate, you will use the region under the curve and above the curve and subtract them together. The same idea if we do the length, right? So the length here, this length longer than this length, longer than this length. So keep in mind that the length here, and this is a part of abstract, and you have to think a little bit and say, okay, my length here is changing, my function of length here is changing. And how it's changing? It's changing by the curve, shape it by the curve. Sometimes long, sometimes short, depend on the curves. And it will be depend on the difference between the two curves. So I'm going to say here, the length is changing, right? It's changing and can be found by the differences, right, by y2 minus y1. These are the two curves shaping this length, right? One above and one below. So the difference between these two curves is shaping the length, sometimes long, sometimes short, right? So you will use to find that length, you will say, therefore, y2 minus y1 will be equal to the length of our cross-sectional area, right? I hope that I explained very well about this imagination concept, right? So now all what we do is to find this length in terms of the function, right? We're going to substitute y2 minus y1. So what is our y2? Our y2 is minus x squared plus 11. I'm going to put in bracket. Subtract our y1, and our y1 is x plus 3. Now I have to notice which one is above. This curve is above, right? So I'm going to use the above one, subtract the below one, right? So the above one is this one, and subtract this curve is the below one. Remember the differences between them result in shaping the length as well as the width of our cross-sectional rectangle. That's all it's about, right? Okay, so now I'm going to simplify this length, right? After we establish the length function, and the width is the same, right? But we were talking about the width later. So let's summarize the length here. We have minus x squared here, so it becomes minus 2x squared. Plus 11 minus 3 will be plus 8. So that is the length function of our cross-sectional area. So now I'm going to figure out what is the width of it. Now remember, the width is based on this sentence. I frame it here. The side of one length is 4 times longer than the other side. So our width function will be based on this one, right? Except that we will divide it by 4, and I'm going to put it in front instead of divided by 4. Everything inside is just the same, like the length, except that multiply with 1 over 4. The same like you divided by 4, okay? So now I have the length, the width. So now it's getting a little bit easier. We can use the area equal length times width, right? So our cross-sectional area will be equal length times width, which is will be equal 1 over 4, this is the width, minus 2x squared plus 8, multiply with the length, which is the same, minus 2x squared plus 8, except we don't have a 1 over 4. So this is the width and this is the length. Now I'm going to join these two brackets together, right? In my way I'm doing that so that it's easier to calculate. So I'm going to make them become one bracket because they're exactly the same, right? Minus 2x squared plus 8. So 1 over 4 is still there. Minus 2x squared plus 8. I'm going to power it by 2 if I join them like that, right? So now I'm going to say, okay, so at this point, we know our area of the cross-sectional function, which is this one. Our next task will be, instead of doing some sum, right? Which is we slide so many strips, like so many rectangles, and we find the total of it. When we take the limit, when the number of strips is approach to the infinity. But doing that is a lot more complicated than using the iteration. The iteration technique in calculus allow us to find the volume in a very easy way, right? And therefore, we're going to use the easy way. We're going to be lazy today. We're going to use the easy way, okay? So we're going to use the iteration. Now, to find the iteration of this cross-sectional area times with delta x, right, and dx, will give us the volume. We have to figure out the boundary, the interval, from where to where we generate the function, from A to B, right? But how do we generate it? How do we know A and how do we know B? We know it from the intersection between these two curves. So these two curves intersect at 2 points here. That will define the boundary we generated because we generate this region, right? And the region bounded by the front point and the end point here. So the front point here, we have to find it, actually, assume that we don't know number, right? And actually in the given information, they didn't tell us how much. So we have to find the intersection. If they tell us, then we know, but if they don't tell us, we have to find it, right, by ourselves. And how do we find it by ourselves? We'll set up this curve equal this curve. Once they equal, the coordinate of x and y here the same for both of these two curves. So we're going to set them up equal, right? So we will say set y2 equal y1 to find what? A and B, right? So what is our y2? Our y2 is minus x squared plus 11 will be set equal with our y1 is x squared plus 3. So solve this quadratic equation, we'll be able to find out our x coordinate and our y coordinate as well if we want, right? But in here, we only need the x coordinate. Okay, so let's solve it. I'm going to move this x squared to the right-hand side. When I move, this become positive, so I add to this will become positive 2x squared. I will move this 11 over here as well. So minus 11, when I move, positive become negative. So minus 11 plus 3 will be minus 8. Minus 11 plus 3 equal minus 8. And that equals 0, right? When we move everything to the other side equals 0. Now I'm going to solve for x. So I'm going to factor out the 2. I have 2x squared minus 4 equals 0. I'm going to factor out one more time. We will have x plus 2 times with x minus 2. And that's based on how we solve the quadratic function. I guess everybody know about this when we go to calculus. So I go through it a little bit more quickly, right? So it turned out when we set each of them is equal to 0, we solve, we have x1 equal minus 2, and we have x2 equal plus 2. So now we know this cross section here, the boundary here is minus 2. This should be minus 1. So minus 1 should be here. See. Plus 1, and this is 2. Yeah. Okay. So now we know so now we know A and B, right? This is our A and this is our B. So we're going to substitute the A and B here, and we're going to substitute the area function in here to do the integration. And our integration will go from minus 2 to 2 interval. So let me erase some of the part here so that we can continue. So I'm going to erase this here. Okay, so we're going to do the integration from now we know this is minus 2 and B is 2. We're going to substitute our area function in here, which is 1 over 4 times with minus 2x squared plus 8 and power 2. And we will integrate dx, right? Now I also can put this outside if I like, right? It's constant, I put outside. And I'm going to simplify the inside bracket here. So let me do that. So this is our A, is our B. Assume the whole thing here is A, the whole thing here is B. I'm going to use a formula, right? It will be square of A squared, which is positive 4x squared, times minus 2 times A times B. That's the sign of the formula, right? Minus 2 times A times B. 2 times A times B is 2 times A 16 times another 2 is 32 x squared. And the last term will be square the B squared, which is 64 dx. So now I'm going to perform it antiderivative, right? And this is minus 2 and 2. So antiderivative of this, how do we do antiderivative? Remember, antiderivative means we add one more power on the top, and I guess everybody still remember, right? So we'll put 1 over 4 here, bracket. This will give me 4 divided by 3 x to power, and wait a minute. This term, do I make mistake? Yes, the x squared, so when I square it, it should be x4, right? Therefore, I missed anything? Yeah, I just missed it here, right? So 4x to the power 4 minus, yeah, this is x squared. This is, yeah, okay. So now minus 32 divided by 3, x to the power 3, adding with 64x. And close the bracket, when it generates from minus 2 to 2, minus 2 to 2. So I have to continue it here. So I'm going to erase this part. Okay, so I am going to continue on here, on this board. So this, I'm going to put it here, 1 over 4, and we have 4 x to the power 5 over 5 minus 32 x to the power 3 over 3, adding with 64x, and from minus 2 to 2. So everything here will be substituted by 2, right? So 2 here will be 2 to the power 5 over 5 minus 32 times 2 to the power 3 over 3, adding 64 times 2, and minus another bracket, which is exactly the same, 1 over 4, and 4 times minus 2 to the power 5 over 5 minus 32 times minus 2 to the power 3 over 3 minus 64 times minus 2, actually adding. Okay, so let me cancel this one with this one. We will get 32 over 5. Minus this 32 cancel with 4 as well, will be 8 times 8, which is 64 over 3. This will be 64 divided by 4 will be 16 times 2 is 32. Minus this cancel. So that is minus 32 over 5. But minus with minus will become plus. This will be minus 8. Minus 8 times minus 32 is become plus. But plus with minus, right? See minus will be minus 64 because cancel with that over 3. And this is 100 minus 128, but minus will be plus. Now 64 divided by 4 is 16. So this will be plus 32. Okay, so these number exactly the same, right? You can see that. This is plus, the minus, same number, is plus. So I'm going to just use one of them, multiply with 2, okay? Because they look exactly the same. So I'm going to times 2. So now let me calculate it out. So 32 divided by 5 will be equal to 6.4 minus 64 divided by 3 will be minus 21.33 with the bar on top, adding with 32. So 6.4 minus 21.33 at 32. The answer is 17. So this will give us 17.06. but time with 2. So this number will multiply with 2, give us 34.13. That's the answer for our volume cubic unit. So that's the idea. Okay. Now I'm going to, before I move on, I'm going to simplify this question to you, right? So let me simplify it so that you remember a little bit, right? I'm sorry for the light here, and I cannot get rid of it. I'm sorry for that. Okay, so there's a light shape in here, shining here. I don't know how to fix it because if I turn it off, it will be too dark. And if I turn it on, that has happened. And it's on the top of my ceiling. So no way I can do about it. Sorry about that. But let me give you the general idea of what we're doing now today, right? So the question today say that we have a two curve which is intersecting each other at 2 points, result in the region between them. The question asks us to revolving this region about the x-axis by and finding its volume using the cross-sectional area. And our cross-sectional area today will be rectangles, not this. Even though we use this method, we do it, but we're not going to cut it through the disc. But rather than that, we slide this many slides by the rectangle shape. So our task is find the volume. To find the volume, we use the cross-sectional area here, times with the delta x, which is the height of the the height of the object, right? Keep in mind delta x, the height of the object, and the whatever it is the function. The rate of change of these two curves is not the fixed number. So we apply find the area of rectangle by length times width. Keep in mind that our length and our width of each rectangle cross-sectional area here were changing by the two curves. So therefore, if we use the first curve, we minus the second curve. That is the length of our rectangle. As well as, so we're talking about the length first, right? And then after that, the question say we can find the width by shorter than the length 4 times, right? So we divide by 4, we get the width. So we have to find the function that shapes the length of our cross-sectional area by using y2 minus y1. So after we get the length, we know that the width will be the same, except that we divide the width by 4. So the part of it were erased already by me. So after we simplify that, we get into the area function, which is this one here. And we have to find the intersection of the interform. Where do we generate this? From where to where? So our A to B will be minus 2 to 2 by setting up these two functions equal and so on for x. So we get the intersection, right? And then we put in the iteration from minus 2 to 2. And we put in that and we generate this function. We do antiderivative, and everybody already know the procedure of antiderivative, right? So we're going to change this x4 become x5, we divide by 5. Change this x2 become x3, we divide by 3. This becomes 64x, and we substitute in and we get that answer. So actually, not bad, right? For the question and the way we do it by using the iteration. So before I end the video here, I'm going to remind you a little bit. please understand that my lesson plans and my way of teaching, I progress through the beautiful language of math naturally, universal language of math, which is it built up by progression. And in any course, actually music as well, right? We do do, re, mi, fa, sol, la, si, do before we make them become a beautiful tune, rhythm, right? So the same like math language, right? You build from alphabetical A, B, C, D, the same like English, we learn any language. So therefore, if you follow me on YouTube in the order of my lesson, that's great. You can learn it free. If you don't follow me on the YouTube, you can go to my website. I will post my weekly lesson plan to this website, mymathteaching.ca. Now, keep in mind that when I make the course online and when I make this website, I have to pay for it, right? As well as putting my stuff on YouTube, I have to pay promotion as well. So to deliver my labor to you for free, I have to cover on the expense I make up for online courses as well. So I sell my course at a very cheap price compared with my labor, what I put in there. But I guess we are reform educational online now a lot. And we try to give out, contribute our labor to the free educational online to earn the students around the world. And we like to do it. I like to do it because that's my expertise and my skill, my experience. So I want to do what I be able to do. And I share my passion to you. So I need the energy to go to continue to do all of this. And if you like my video, please visit my website and learn the weekly lesson. Of course, you will only learn if you are in a calculus course. But in the future, I will make some more course in grade 9, grade 10, grade 11, and so on, blah, blah, financial mathematics as well. So to be able for me to contribute my labor, I should help out on the student. I should ask for a little subscribe to my channel or donation, right? Compare with the private one-on-one tutoring lesson is still so cheap. And therefore, I wish I was in this generation to be able to learn what you are learning now on the YouTube. And any teacher, any professor can show you, and you don't have to pay for it. Very expensive, like the way we have to learn before. And in the past, I would never have a chance to pay for my private tutoring, to be honest with you. And therefore, I found it's very useful and necessary if we can provide on the students and bring the equality in education to the whole world. So I like the idea and I like the way we change in the educational reform now. Online education is the best, I think, because you get the private one-on-one lesson plan without paying for it. So I just ask you a little bit donation. I don't think it's too much compared with what I put in my courses online and to help all of you out. Some of you might feel it's useful and you have a lot of teacher, professor to learn from, not just me. I understand that, but it depends on your learning style. You will find maybe one of us appeals to you, and the way you explain, we make the lesson maybe will be easy to some student and maybe difficult to others. It all depends. But overall, we try our best to provide you a qualified education online on YouTube. And therefore, if you support us, I would appreciate. So if you can go to mymathteaching.ca and visit my website, and if you follow me, you can email me as well. I might not have time to answer on the email, but I will try my best and to satisfy your curiosity if I do have time. And so I just remind you about that before I go. So thank you for watching, and I hope you enjoyed my video, and will stay tuned for the next video. We'll get into the shell me thought, which is a lot more interesting. See you. Bye for now.